Okay, this section is on Cholesky factorization. And we're going to start with the square root, talking about square root of a matrix. So if I have B is equal to B Hermitian, and if B Hermitian is positive definite, actually for a square root we only need positive semi-definite, then we can compute the square root of B as Q times QH. So we write B as Q times QH. Oh, by the way, so remember that B is positive definite. B is positive definite if and only if, YH BY is greater than 0 for all Y not equal to 0. So that's what it means for a matrix to be positive definite. Hermitian, of course, means that if when you transpose and complex conjugate, you get the same matrix back. Okay, in that case, we can take the square root of a matrix. But the square root is not necessarily unique. So, for example, here's a B. Now, this particular B is positive semi-definite because if I do, y1, y2, y1, y2, I get y1 squared. And this thing, it's possible for this thing to be, it's equal to 0 when y is equal to 0 alpha. So, which is not necessarily 0. So B is simply positive semi-definite, or we would write greater than or equal to 0. Okay, so in this case, we can look at two different square roots of B, and maybe even to make it more interesting, maybe we should make this, instead of 1, make that a 9. Then you could have a 3 here and a 3 there, and this matrix is a square root, or a 3, 3, and those are both square roots of B. So both, this 2 by 1 matrix and also the 2 by 2 matrix are square roots of B. Okay, so square roots are not necessarily unique. All right, so now let's come to the Cholesky factorization. So the Cholesky factorization of B will be in this particular case, we're going to insist that the Cholesky factorization is square. Okay, so in the previous example, the square root didn't necessarily need to be square. We had one that was square and the other that was not. For the Cholesky factorization, we're always going to compute a square root of B. And it's also going to be lower triangular, okay? So in other words, the square root will have zeros in all of the elements above the diagonal. So in that case, we can write B in terms of L as L times L Hermitian. Now notice that if you were to let L equal UH, then you could also write this expression in terms of UH times U. And it turns out, like in this book, they use lower triangular L times LH because it actually turns out to be a little bit more convenient for stochastic processes. But in Matlab and in Python, the Cholesky factorization algorithm returns an upper triangular U. And so in that case, you can go back and forth by just taking the Hermitian of the matrix. All right, so let's kind of set the groundwork for how we do Cholesky factorization. So given any matrix B, it's symmetric or Hermitian. So we know that we can decompose B as follows. So this is the 1, 1 element of B, and then we've got the first column. The rest of the first column is going to be little v, and then because it's Hermitian, you've got VH along the top row. And then the rest of that matrix we're going to call B1. Now notice that we can factor B as follows. And just to kind of illustrate that, let's just multiply out these matrices. So when we multiply square root of alpha times 1, 0, 0, we get square root of alpha. And then on the top row, we're going to get 0, 0. And then on the bottom left element, we're going to get v over square root of alpha. And then on the bottom, we get b1 minus vvh over alpha times square root of alpha vh square root of alpha 0 identity. And when we multiply this out, we'll get alpha and then vh v and then we'll have vvh over the square root of alpha plus b minus vvh over the square root of alpha. And of course these cancel out, and we just get our original matrix B. Okay, so now we want to start looking at doing the the idea is that we're going to do a recursive factorization of B. So if we let, on this previous slide, if we let this guy be equal to G1 G1H, for example, then and we do, in other words, we do the Cholesky factorization of B1 minus VVH divided by the square root of alpha. If we can do the Cholesky factorization, then this G1 comes over here, just G1H comes over here, and we can factor B in terms of these two matrices. And notice that this matrix here, so alpha is the 1, 1 element, and then G1 is a lower, if we do the Cholesky factorization, G1 is lower triangular. So the upper triangle is all 0, and this guy becomes the square root of B. So the Cholesky factor is, given by this matrix, square root of alpha, V over square root of alpha, G1. And this forms the basis for our recursive algorithm. So let's do an example and show how this works. Okay, so here's B, and the first thing we're going to do is basically think of this as dividing that up. This guy becomes, let's call it alpha 1, and this guy is V1. Of course, it's symmetric, so that's V1H. And then this matrix here, this 3 by 3 submatrix, we're going to call that B1. Okay, so we've written B in terms of alpha 1, B1, and B1. And here's our, here's the way we've defined everything. All right, so now we come down and let's write B in terms of this factorization. So alpha, notice, recall alpha is equal to 1, and let's just remember V is 2, 4, 1. So the square root of alpha is 1, and then V over the square root of alpha is 2, 4, 1, and then the VH up here. And then I've got this lower triangular, this lower block will be the Cholesky factorization of B1 minus V1, V1, H, V1, I guess these are all real matrices, so V1, V1 transpose divided by the square root of alpha. So let's plug in B1. Remember, this is B1, the 13, 17, 18, etc. So there's B1, and then we have to, alpha is 1, so minus square root, 1 over square root of 1 times V1, V1H. When I multiply all that out, I get this guy. Okay, so this is going to be G1, G1 transpose, and now I need to do the Cholesky factorization of this matrix. So let's look at that. And again, I'm going to simply divide this guy up. That's going to be alpha 2. This vector is going to be V2. And then this guy is going to be B2. So again, I've written it in terms of, this factorization here. And now alpha 2, if we go back, alpha 2 is 9. And so the square root of alpha 2 is 3. And then V2 is 9, 6. And I'm going to divide by the square root. So divided by 3, I'll get 3, 2. And that's, and that's going to give me my V2 over square root of alpha 2. And then the transpose. And then I've got, the Cholesky factorization of this lower 2 by 2, which is going to be B2 minus a V2 transpose over alpha 2. And I plug in what alpha 2 is. Remember, alpha 2 is just going to be the 13, 12, 12, 29. And so that's that matrix. Over 1 over square root of 9 times V2, V2 transpose. When I multiply and add everything up, I get this guy. And now I have to do the Cholesky factorization of G2, G2 transpose. So again, I'm going to divide like that. This is going to be alpha 3. And now my vector here, V3, V3 is just a scalar. It's a 1 by 1. And then this thing is going to be B3. B3. All right, so now I come to do the Cholesky factorization of G2, G2 transpose. So G2, G2 transpose, I'm going to do the square root of alpha 3. Remember, alpha 3 is 4. And so I get my square root is going to be 2. And then I have V3 over the square root of alpha 3. V3 is 6 divided by 2. It's going to be 3. And then I've got the 3 up here. And then I'm going to have G3, G3 transpose, which is the factorization, or which is the Cholesky factorization of B3 minus V3, V3 transpose over alpha 3. B3, remember, is 25. Okay, so there's 25 minus 1 over square root of alpha times V3, V3 transpose. Multiply and add, I get 16. And that means that, so in other words, I have G3, G3 transpose is 16. So G3 is obviously 4. Okay, so at the end, once I get down to the final value, I just take a normal square root of a scalar, and now I've computed, there's G3. Now I can come back here and get G2 because I know G3, and then I can go back and get G1 because now I know G2, and then I can go back and get my factorization because I know G1. So I'm going to just plug that all in here. L is going to be, from the first step I had L was this guy, and then I found G1. It's going, at least I found the first row and column of G1 in terms of G2, and then I found G2 in terms of the first row and column and G3. G3 I found to be 4. So I just now have L, which is the Cholesky factorization. And you could plug this in to show that A is equal to L transpose. Okay, so that is the algorithm for doing the Cholesky factorization. Now let's talk a little bit about some of the places that we use Cholesky factorization. So for example, suppose that I've got this quadratic form, xHQX, which we denote as the weighted 2 norm of x. And suppose that Q is Hermitian, then we can write Q in terms of its Cholesky factorization, UHU. So we write it in this way. And then, that is just the normal 2 norm of U times X. So in other words, weighted 2 norms are just like taking a normal 2 norm where we multiply by the Cholesky factor on the inside of the normal 2 norm. Simulating a random vector. So this is something that comes up all the time in applications. Suppose you're doing something in Matlab or Simulink or Python or C++ or some kind of simulator, and you want to get a Gaussian random variable with covariance equal to R. Covariance matrices are always symmetric, and so the covariance of R will equal R transpose, and covariance matrices are positive definite. All right, so how do you actually produce a you specify R, how do you produce a random vector that has covariance equal to R? All right, so Matlab and Python, and there's going to be C libraries as well. Matlab has this function rand_n, and if you give it, if you say rand_m n and you give it dimensions m1, it's going to return an m×1 random vector that's normally distributed with 0 mean and covariance identity. So that's what rand_end will do. It gives you a covariance of identity. So now we want to have, so to change the mean, we could just simply add in mu. To change the covariance, how do we do it? Well, to generate, let's say, a 0 mean, normally distributed random variable with covariance R, first let R, find the Cholesky factorization of R in terms of L and L transpose, and then let Z equal to L times X. Okay, now Z is going to be, I'm claiming that actually Z is going to be 0 mean Gaussian random variable with covariance R. So we just simply multiply by the Cholesky factorization. And to show that in fact Z has covariance R, you look at the so the covariance for a 0 mean random variable, the covariance is just the expected value of Z times Z transpose. So we know that Z is equal to Lx, so that's the expected value of Lx, X transpose, L transpose. And now X is random, but L is just a matrix, right? And so we can pull L and L transpose outside of the expectation, and we get L expectation of X times X transpose times L transpose. Well, and this is the covariance of X, which we already know is identity. So we'll have L times identity L transpose, and LL transpose is equal to R. So in fact, the expected value of ZZ transpose is R. So this is the way you generate a random vector with covariance R. You basically find the Cholesky factorization of R, and then you multiply the 0 mean covariance of identity random variable by the Cholesky factorization, and that's going to produce a random vector that is distributed in the way that you want it to be. Okay, we can also use Cholesky factorization to solve the normal equations. So the normal equations, so you get the normal equations anytime you're solving a least squares problem or a min norm problem or a dual approximation problem. So we end up with this, R times C equals B, and R is a Gramian, so it's Hermitian. And if the data vectors are linearly independent, then R is full rank. So typically you end up with something like this where you have a full rank R. Now if you let R be, you do the Cholesky factorization of R in terms of L and LH. Then this normal equation becomes LLH times C is equal to B. So we do our little trick here. We let Y equal to LHC, and we solve Ly equals to B. So in this case, yeah, Y is equal to LHC. And this is actually easy to solve because it's a lower triangular matrix. So we can solve, the first element we solve for y1, and then y2 will be in terms of y1, y3, etc. So this is easy to solve. We don't have to invert any matrices. We just do it by forward substitution. And then, then we've found y. And so y is equal to LHC. So we can rewrite that, LHC is equal to y. We've found y, and we know LH, and now we want to find C. And so LH is going to be, upper triangular, so we would do backward substitution. So xn will be easy to solve, and then xn minus 1 be easy to solve in terms of xn, etc. And you can go ahead and solve this equation through a backward substitution, meaning starting with xn, going backwards. Okay, so if we can find the Cholesky factorization of R with these normal equations, then again everything becomes really easy to solve. And you saw exactly how we did the Cholesky factorization. Turns out to be a very easy numerical algorithm, and it can be done extremely fast. Okay, so another application Cholesky factorization is in Kalman filtering. Actually, it's a kind of a core piece with unscented Kalman filtering, for those of you who've looked at the unscented Kalman filter. But let's just even look at the Kalman filter. With the Kalman filter, we propagate two items. And if you've never seen the Kalman filter, that's okay. I'm just giving some examples. We'll never actually do this in a problem or whatever. So the Kalman filter propagates the mean of a distribution and the error covariance. That should be pk, where the error covariance is symmetric and positive definite. Now, if it's implemented directly, numerical error can cause the covariance matrix to become indefinite, and that causes large errors in the estimate of x hat. So to avoid this problem, you can do what's called a square root Kalman filter. And with a square root Kalman filter, what we do is we do a Cholesky factorization of the covariance, and then you find the propagation equations for the Cholesky factorization, and you propagate the Cholesky factorization. And then even if no matter what, because of the way it's constructed, pk is guaranteed to be symmetric and positive definite. Okay, so in Matlab, there's this function chol of a, and we have to do the tick here at the top takes the Hermitian of this matrix, and so Cholesky prime, I guess, will give you L. In Python, there's part of the SciPy library. Actually, I think there might be a part of the NumPy library as well. But anyways, as part of SciPy, you've got the linalg.cholesky, and it returns. Actually, I think this returns U, so I think you would have to do a dot conjugate transpose, and then that will give you the lower triangular part. Okay, that's it for Cholesky factorization.